So, as we have discussed till now in this course, right, that there are mainly two ways in which electricity produced by solar photovoltaics, right, gets utilized. One of the way is where it's a standalone system where the energy is first stored in batteries or maybe some other form of storage and then gets utilized by local loads. The other way of utilizing the solar energy electricity is where the electricity produced by solar is directly fed to the grid, and then it gets utilized by other loads connected on the same feeder or on the nearby feeder or a little bit further away in the grid, right? So, and as we understand, the second mode is the most popular one because of the reasons such as it can use the existing grid infrastructure, right? Therefore, there is no additional cost of storage required, which is the case with mode 1. So although yes, it can use the existing grid infrastructure, but then it could potentially create challenges for grid operation, protection, and so on. So in this particular discussion, let us talk about how the grid inverters were supposed to be controlled, right, when they started operation, and with those kind of preliminary controls, what kind of challenges does a usual grid or a distribution system faces. So these are the three documents which I have used as reference to create this particular video. In addition to that, I have also used some of the figures from these three documents, right, to demonstrate some of the basic principles or the basic issues and challenges arising because of solar. So let's get started. Now, if you see the when the solar PV started, the expectation, I mean, obviously the prices of the panel were high, right? So they still did not reach grid parity. So the expectation was that yes, solar can definitely be connected onto the grid, but because they were not economically very viable at that point, the expectation was the total amount of solar that will get installed would still be a minor fraction of the total grid installed capacity, right? So the expectation was there's going to be small solar and still predominantly by either by coal or gas or by nuclear or something like that. So the initial requirements of the solar inverter, the grid feeding solar inverter, was also set accordingly, right? So what were the initial requirements? The initial requirement, one of them was on the total harmonic distortion, right, and the individual current harmonics, right? So if we have a inverter, right, if you have a panel connected feeding to an inverter which is feeding power to the grid, it was expected that the current that the inverter is feeding into the grid would have low value of total harmonic distortion, and also the individual harmonics, right, for especially the lower ones like third, fifth and seventh, would also be restricted to a low value, right? So why was this needed? This was mainly needed because if by any chance the current fed by the inverter has harmonics, in that case, if this is the feeder, right, this is the substation transformer, this is the feeder, and now if you have a solar inverter connected at this point, right, let me call it as solar inverter SI1, and if it starts feeding harmonics, then the harmonics will interact with the impedance of the feeder and will create harmonics in the voltage available at the load end, which can then affect other loads and the other systems connected to that feeder. So that was predominantly the reason. The initial thought was that let the solar inverters not pollute the grid. Excuse me. Let the solar inverter not pollute the grid, and let them ensure good total harmonic distortion, by mean good a smaller value of total harmonic distortion of the current. On similar thought, the reactive power was also not allowed to be supplied or absorbed by the inverter. So the initial idea was that these inverters should operate at unity power factor. Now same thing, right? So for instance, there is a certain load. If the inverter starts drawing a lot of reactive power, then one may have to then install an additional capacitor banks and so on, and therefore initially it was asked that all the inverters must stick to feeding power at unity power factor, so that it does not create any additional voltage drop because of the reactive power that they may start drawing, right? The other next thing was, because again the unity power factor was set in, they were not expected to do they were not expected to deteriorate the voltage profile, and they were not expected to either help in improving the voltage profile. So they were just asked to feed power at unity power factor. The third major thing was the anti-islanding, right, which is that if the grid fails, right, then the system, the inverter connected in the system must also disconnect, right? It should not produce an island of its own. It should disconnect as soon as possible, right, if the grid fails. Now this is the grid failure part, but a lot of times what happens, right, that there is a transient and momentarily grid magnitude, frequency, voltage might go out of bound, right? And in those cases also it was asked for the inverter to disconnect as soon as possible. Now the philosophy could be something like that, right? For example, if there is a disturbance in the grid, then the solar inverters might end up making the situation worse. So it is best if the solar inverters disconnect and the grid continues to operate with its basic controllers and the basic power generation systems. So this might be the philosophy, and therefore there was fast acting over voltage, for example, under voltage, right, over frequency protections which were supposed to be there in the inverter. So for example, if over voltage, if it goes above, let's say 1.1 pu, right, then suddenly disconnect. Under voltage, if the grid voltage goes below, let's say 0.85 pu, disconnect. Over frequency, let's say it goes above 50.2 or 50.3 hertz, right, disconnect. So all of these were intentionally meant so that the inverters was being looked at an external device, and it was best evaluated that if in case of any disturbance, these inverters, it's good if these inverters disconnect and the main process is handled over by the conventional generators. Over the time, what happened was, now these things were good, as we discussed, if it was a low penetration system, right, low PV percentage, right, as compared to the total generation capacity. But over the time, that has not remained true. The main reason has been the continuously reducing cost of solar photovoltaic panel, right, the concerns for climate change and so on. So now the picture of PV that most of the grid is looking at is continuously growing, continuously increasing penetration of PV in the system. So what kind of challenges can it bring? Right now, here in this discussion, I would categorize these challenges as in two broader categories. So one of the category is feeder level, and the other one is grid level. Right? So what essentially it means is that some of the challenges, or rather what are the challenges at the feeder level, at the distribution level, right, because of solar photovoltaic being connected to the feeder, and what are the challenges at the grid level because of these photovoltaic getting connected in the system. So let us first start with feeder level challenges, and then towards the end we will touch upon just a few of the grid level challenges. Now, unlike conventional generation, a conventional generation would all get connected at a relatively higher voltage into the system, right? They were not necessarily very close to the load end. So conventional generators were farther away. They would generally get connected using a step-up transformer, connect to a relatively higher voltage, and then the power gets transferred to the load ends. But solar, on the other side, gets connected predominantly at the low voltage side, at the distribution side. Right? To give you an example, this is from one of those 3 articles. This is the graph which shows the solar connected into the system, into the grid in Germany, right, at different voltage levels. So you see that the yellow is the solar, and sorry, yeah, if you see that the majority of the solar gets connected at the low voltage, right, which is 400 volt level, and yes, there is some solar getting connected at between 10 to 20 kV, but as we go up in the voltage level, the contribution of the solar becomes very, very small. Although things have changed now, recently there have been a lot of news and articles about connecting or building large power plants solar, which would directly then connect to a significantly higher voltage. But that is true, and that would coexist. But at the same time, this graph indicates that there's going to be a lot of solar penetration in the end distribution system, right? Because a lot of houses may have solar, a lot of small industries may have solar, rooftop solar, and they may all be feeding power into the grid. So this specific feature of solar brings an additional challenge, which not existing, not heard before. To some extent, wind, yes, unlike conventional generation, wind was probably expected to be there in the distribution system, but again, wind is again not something which people connect at 400 volt level. It still is a relatively higher voltage, unlike solar, which could really bring that challenge. So because of this unique feature, it also brings some amount of challenges into the system. So therefore, let's first focus on the feeder level, right? What is at the lowest voltage level? What kind of challenges does this solar photovoltaic brings? Now, if you see in a feeder, right? Let's say this is a transformer which is feeding to a feeder where this is, let's say, some load L1, L2, and there is some generation happening here, which is solar photovoltaic 1, right? Now, if you see at this point, right, at the substation level, and if you monitor the power here, so typically the power versus time graph of the load could be a certain fashion, right, depending on what is the weather season and so on, right? I've almost plotted it constant. It could be a small variation, but then the power, this is the load power, right, and the power by the solar photovoltaic 1 would be something like this. So during the day it will rise, and in the evening and in the early morning it would become 0. So therefore, if you see the net power, what is the net power? Net power is the difference of the two power. If you see the net power that is drawn from the grid, which is load power at any instant, minus the solar PV power, then the net power graph would look something like this, right? You see that there is, if the load profile would have been constant, there would have been a dip in the demand of power during the day, because during the day solar generates the most. In fact, the actual graph is a little bit different from this, right? It's not flat. So the actual graph looks something like this. So I'm showing you again another picture from one of those articles, which gives us an indicative graph. So if you see 0%, right, the line corresponding to 0%, that is actually the load requirement of a particular feeder, right? And if you see the load requirement of that feeder, it is varying during the day, right? In the evening, you see that it really goes up, which is possible, you know, depending on, let's say, if it's a mix of residential and some amount of commercial, then in the evening both of them may start consuming electricity and power, and therefore you may see a little bit of peak. Now if you see, if we keep on adding solar into this particular feeder, right, let's say we add 10% solar, then the graph changes, right? If you add 20%, then again it dips further, you get this green graph. If you see this green graph, it looks something like a duck, right? And that is the reason this is called as a duck curve. What it tells us is that yes, we need a majority of the power, the peak demand actually comes in the evening, but unfortunately solar does not also supply power in the evening, but then solar brings down the power requirement during the day. And eventually what is going to happen is, if we keep on adding solar, as you see in this graph, the power starts becoming negative during the day. What it tells us is the time instant at which solar is producing power in this feeder, the load in this feeder is much less, and therefore the total power becomes negative and the total power starts feeding back to the grid. At the same time, the peak requirement of the power of the feeder, which comes in the evening, still remains more or less the same. So although solar is helping in terms of producing energy, but it is not helping as much to that particular feeder, because that feeder needs power in the evening, right? So what happens because of this? Negative flow of power, let's say during the day? For example, here if you see, let's say between 11 a.m. to 3 p.m., right? If the power is flowing back into the feeder, then what happens because of that? What happens to the voltage profile in the bus? So let's consider a system, right, where something similar to this, where you do have a big feeder, right, and you have solar photovoltaic connected, let's say multiple of these in the system. Now in the conventional feeder, as we understand, if there is no generation, right, if the power flows from left to right, in that case, as we keep on moving farther and farther, the voltage reduces, right? So for example, each of the load draws some amount of active and some amount of reactive power, right? Then the voltage V1, V2, V3, V4 keep on reducing, because all of this P and Q gets multiplied with the impedance and creates a drop, and further the second load creates additional drop, and so on and so forth. And that is the reason conventionally we would actually add some capacitor banks, right, in between in the feeder, so that we can again pull up the power, pull up the voltage level. So let's see this graph, right? Focus on the blue graph first. On the y-axis we have the voltage in the feeder, and on the x-axis is the distance of that feeder, right? The distance we would cover in that feeder starting from the substation. So you see, substation voltage is well maintained to 1 pu, which could be done by using, let's say, an on-load tap changer transformer at the substation. Now after that, as we move along, if you see the blue one, the voltage is continuously reducing as we are moving farther and farther away in the feeder. So blue one is without cap. If you add cap, right, at specific locations, one can actually ensure that the voltage profile in the feeder is almost constant, right? The voltage profile, as we move along, the distance still almost remains constant. But now if we have PV also in the picture, And imagine the scenario where the net power is negative. That means this feeder is exporting power. In that case, if the solar photovoltaic is, let's say, connected, distributed into multiple buses in the feeder, then the total power is going out, and therefore the voltage at the farther end of the feeder will start going up as compared to the substation, right? So this is now something which has become very specific to generation happening within the distribution system, right? The voltage profile within the feeder has changed. The overall voltage has also changed, right? But more so the profile has changed. So earlier, where the capacitor used to solve the problem, here the capacitor bank may not be of much help for this kind of situation, right? In fact, those capacitors might be probably get deactivated, or probably would be deactivated, right? And still the problem of voltage increasing as we move along the feeder might remain. So such kind of problems can occur. For example, if the solar inverter is operating with the basic principles of unity power factor operation, right? Maybe in some of the subsequent videos we'll also see some of the ways how these problems can be solved. But I think in this discussion, let us keep on talking about the issues and the challenges, and then maybe subsequently we'll see how to solve those problems. Now this is one. Now let's move on to the second thing. What about loading, right? What about loading? Earlier, let's say this is the picture. This is the same feeder we are looking at, right? So V1, V2, V3, V4, and solar is connected at the end point, and there are loads which are connected. So now conventionally, if there is no solar photovoltaic, then power will flow from left to right, and as we are moving from left to right, the power handled by that particular section. So let's say this is section 1 of the feeder, this is section 2, this is section 3. So as we move from left to right, the power handled by each section is reducing, right? Because the leftmost section S1 has to supply to load 1 as well as to load 2 as well as, let's say, to load 3. But the section 2 only has to supply to load 2 and load 3. Section 3 only has to supply to load 3. So as we are moving farther away in the feeder, the load handling is reducing. But on the contrary, if we have solar photovoltaic, and consider the situation where the same situation in the afternoon in the duck curve where the total power is negative, in that case what is happening is the solar PV is producing significant power. Small part of it gets utilized in load 3, small part of it gets utilized in load 2, some of it gets utilized in load 1, and the remaining goes back to the grid. So now if you see which section of the feeder is handling most amount of current, it is section 3 which is handling most amount of current. Why? Because section 3, the power flowing through section 3 has become maximum. It's in the reverse direction, but the magnitude is maximum, and further gets reduced little bit in S2, further gets reduced little bit in S1. So what does it say? The initially, let's say the feeder is designed to feed only the loads. In that case, it may not necessarily be suitable for if a solar photovoltaic is connected at the end of the feeder. So this kind of problem is another problem, which again would require, let's say, some kind of maybe reinforcement, right, of the feeder section, right? Reinforcement or reconductoring. Right, it would require reinforcement or reconductoring of different feeder section. So if you see till now, we have talked about two main things, right? One is the voltage profile in feeder, right? This is one of the challenge that we have discussed, and the second one is the difference in the loading of feeders of different sections of a feeder, right? So far so good. So now moving on, let's have a look at the third problem because of the connection of solar photovoltaic in the system. Now, in both of these problems, we were considering this kind of a curve where the solar power during the day is maximum. But then the generation during the day need not necessarily be very smoothly ramping up and ramping down, right? Imagine a situation where it's cloudy, right? It's a monsoon season, it's cloudy. Then in that case, there is going to be sudden change in the solar radiations, and which would cause sudden change in the power produced by the solar photovoltaic systems, right? Grid feeding systems. I'll give you an example. So if you see this picture, the first graph shows the power produced by one of the solar plants, right? So this particular plant is located at IIT Kanpur, and the y-axis shows you the power, and the x-axis shows you the time at which that power is produced by that particular solar plant. This is the day is 8th of August 2015, right? So it's month of August, it's monsoon season. So if you can see that there is lot of ups and down throughout the day of solar radiation, which is expected. Now, because of this fluctuations in the power generation, the voltage profile in the distribution system may also fluctuate, right? It would certainly depend on what is the impedances of the network of the system, right? And how much power this solar plant is capable of, right? So in this diagram, if you see, the y-axis is only a few kilowatts. So to understand what is going to be the impact if there's a substantial power, we use this data, right, and simulated a system. And the second graph which you see, which is of a voltage profile, is of that simulated system. Here you see the voltage in the feeder is continuously changing, right? And if, let's say, you have a very fast acting on load tap changer, right, then the taps would also change very rapidly, and while doing that, they will try to maintain the voltage within the band. So let me draw the system for you, just for a little better understanding. So the system considered here is something like this. So this is an on-load tap changer, right? This is a transformer where you have multiple tappings on the primary, and what this thing is doing is it's taking the feedback of the bus voltage and then taking a controller action and accordingly changing the tappings of the transformer. And let's say here we do have so here also there is on the upstream also there is an impedance, right? And here also, let's say there's a feeder, and then we do have solar photovoltaic connected here. Let me take a simple situation, right? And we also have a load here. Now what is happening is this P power is fluctuating, right? Because of which this drop is fluctuating. Now this OLTC is trying, and also not just this drop, but because of the drop upstream also is fluctuating, and therefore the voltage at bus 1 V1 is fluctuating. Now this feeder would try to estimate, measure the voltage at the nearby bus V2, and using the impedance and the power flow try to estimate V1 and accordingly control the taps so that voltage V1 remains within the profile, right? And if the OLTC is allowed to operate very fast, which it would not be allowed to, in that case there are going to be a lot of switchings, which is what is visible in this graph. And if it is not allowed to operate, so if it is allowed to operate, then voltage remains within the profile, but then the life of OLTC and the life of the transformer reduces significantly. And if it is not allowed to operate such fast, then the voltages would go out of the normal operating bands, which is also not acceptable. So this is, again, if you see, this is a very specific problem which is coming because of the solar. Now one might say that this is like fluctuation of load, so this also could come potentially because of load fluctuation. But there is a little bit of difference. Yes, it can, but still there is a little bit of difference in terms of the property of solar and of other loads. So imagine a scenario where there is a feeder connected, and feeder is feeding to, let's say, a residential area where there are so many houses and so many loads and so on. Yes, I mean, houses will keep on turning on and off the loads throughout the day. Different houses would do it. But if you see, it's more or less randomized, right? It is not going to happen that suddenly all the feeder load is going to turn down, or it's going to again come back in couple of minutes. Again, it is going to go down in couple of minutes. So it's not expected that this cycle would be very frequent. So that is for the load. But now if you consider, so let me just to give you an imaginary view. Let's say this is that feeder and these are the houses, right, which are connected. And right, so now, so this is what is feeding power to this particular, this feeder is the feeder, right? So yes, so there is some amount of randomization which inherently is present in terms of loads, and therefore the system would not see a sudden repeated change in power because of the loads, right? There may be small perturbation happening every time, but not the major perturbation where all the feeder loads goes down, then again 2 minutes later it again comes up, again goes down, and so on. But now let us look at what happens if it is solar. So now again, you may say solar is also not located at one place. So each house has some amount of solar added into it, right? All the houses have solar photovoltaic on the rooftop, and they have inverters. But it is very likely in this situation that a bigger cloud, right, while traveling would cover quite a few amount of houses in one go, right? And as this cloud is moving, therefore you can see that if the cloud comes up and covers, let's say 40, 50, 60% of the houses, then suddenly the power being produced by the photovoltaics, those photovoltaic panels will get reduced suddenly, and that would create a much bigger perturbation in the power as compared to the perturbation created by the switching of loads, because it's more synchronized, right? And again, when this cloud cover goes away, again suddenly all of those panels will start getting solar radiation and start pumping power. So this power produced by the panel within a distribution system, I feel has more synchronization as compared to the loads which are distributed in a feeder. So this is this is the third problem that we are discussing about with respect to the solar, which is the fluctuations in voltage, right, which could come because of the fluctuations in the solar PV, because of the due to fluctuations in solar power. Now the fourth problem which might come because of solar photovoltaic in a distribution system, in a feeder, is that of unbalance, right? It's in a way it's very similar to the third problem that we were talking about, because if again you have houses where the feeder is distributed among different houses, right? Let's say a three-phase feeder gets each of the single phase goes to a few houses and so on, and now again if a cloud cover comes in, right, during the transient, some of the houses may get covered together and which might cause a bigger unbalance in the system because that particular phase gets lesser power as compared to the other phases, right? So it does depend on a lot of factors, how you are distributing houses, how you are distributing houses onto different feeders, and so on. But this is again a potential problem, especially in a system where solar photovoltaic is connected onto single phase line, right, and not to three phase line. Where the solar photovoltaic is connected to three phase line, such problem may not occur. Now the fifth one, I mean, these three I think are the most important ones. I look at them. Fourth one is again may exist, may not exist kind of situation depending on the architecture, depending on the inverter, single phase, three phase, and so on. The fifth one is in fact not even a problem, but I would still like to write it down here, which is the harmonics. Right. Now, if you recall the discussion, the earlier discussion we had in this particular video, is that this was the first thing which people thought of, right? People thought of, if there's a power converter, power electronic converter getting connected into the grid, they would create issues in terms of harmonics. So this was already sort of fixed, right, at level 1 itself, saying that the inverter should inject current which should have a very low value of total harmonic distortion. But now here, in the way I look at it, is less of a problem and more of an advantage, because these inverters not just can themselves feed a nice sinusoidal current, but if there is a neighboring load which draws harmonics, these inverters can even help the neighboring loads in correcting the overall distortion in the system, right? We will talk more about this particular aspect in one of the later discussions, where we'll talk about utilizing the solar inverter for harmonic compensation. Although as of now it's not very popular, right, still the grid utilities are not really accepting those as solutions. But looking at how things have moved, we have moved from unity power factor to the voltage support and so on modes. It is quite possible that these inverters would also be allowed to do harmonic compensation in the system. So as of now, yeah, fifth is not a problem, but it is more of an opportunity which we are going to talk about later. And these three are the main challenges that exist in the distribution system level. Now let's move on to, we'll talk about the feeder level, which we have just done. Let's see what are the kind of challenges at the grid level. Now, although solar is getting majorly integrated at distribution level, but now again, all of the distribution systems are connected through step-up transformer to the main grid. And therefore, any fluctuations, any changes happening in this distribution system would also impact the main grid, right? And would also impact the generation, the coal power generation, nuclear power generation, and so on. So let us see how these two interact, right? How does these different generation systems interact and what happens there? So I'm going to show you a graph, right, which is so if you see this graph, again taken from one of the three references which I shown before. This is of Electric Reliability Council of Texas, right, ERCOT, of the year 2000, right? So what this graph shows is, on the top you see it shows the load, right, the normal load in the dark black shade, and then in the other black graph it shows the net load, because part of the load is getting offsetted by the solar photovoltaic. So this graph, the load is actually the actual data, right? This particular graph is for summer duration, right? So it's of 1st and 2nd of June in Texas, and the load is the actual load. But then the solar data is actually a simulated data of a 16 gigawatt plant, right? So it's more of a situation that what will happen if there would have been a 16 kilowatt solar plant in such a system. So it's a very interesting study. You can go back and you can read through those references. So in this situation, it looks reasonably good, right? Because it's summertime, during the day, the temperature is high, air conditioners are on in most of the offices, residents, and so on, and therefore the solar, kind of aligns with the peak value of the demand and tries to reduce the peak value. You see, the peak load demand has reduced, as you would see, right? In this graph also, it's clearly visible. The peak load demand has reduced quite a bit, and yes, on the other side, the load demand has further gone down, which is also seems like a good thing to do. And now so this sounds okay. Now let's see what happens if you have the same solar plant, the same system, and we talk about a month March, where the temperatures are much more pleasant. It's probably okay, and some of the air conditioners may not really be working that exhaustively, and this is what happens, right? So now the black one again shows the load for 2 days in a month of March, which is the actual one, and the PV is the simulated power, which is shown. So you can clearly see that on one of the days, the power demand during the day has come down considerably, right? And again, you can see the same thing which we saw just before, the duck kind of a shape appearing in terms of the net load, right? The duck curve becoming more visible here. So what kind of challenge can this for dip in the power during the day can bring? Again, you see, during the day the power is low, again in the evening the power has to again come back, right? Because again all the loads will be on, there's going to be no solar, and somebody has to meet those demand. Now, so who meets the demand in general, right? Before solar, who was meeting the demand? It was the main demand was met by the base load plants. Base load plants include right, base load plants include, let's say, coal, right, nuclear, right? So what does it mean? Base load plants means that these guys will run almost throughout the day at a very high capacity factor, very high utilization factor, right? And they will continuously supply power to the grid. And plus there are going to be some other plants which will can come quickly in action, and they can supply some extra power required, and they can ramp up their power, ramp down their power very quickly. But then these are the base load plants. So those quicker, faster plants could be, let's say, a gas based or a hydro. But these base load plants were responsible for meeting the basic power requirement throughout the day. Now see this situation. What happens here is, in the afternoon, the power demand of this particular network has reduced. Imagine similar thing happening with the neighbor places also, right? With the nearby places also. So in that whole region now, the demand has reduced. Now the question comes that the demand might go below the base plant running capability, right? The base load plants cannot be ramped down very fast. Moreover, they must have a minimum load for them to continue to run, right? There are quite a few challenges. For example, coal power plant, you still have to have suitable control systems. If you go below a threshold of power, then it has to shut down, right? There is no other way on. So there is a minimum operating power these base loads plant will operate to, and below that these plants would then have to be shut down. Now to consider the situation that at 12 o'clock, if this happens and the plant power goes below the base plant, some of the base load plants have to be shut down. Now turning on these base load plant again is a more complex, time consuming, and not so viable process, and therefore people do avoid doing that. So such kind of things might add more challenges into the existing system, right? One of the way to look at it is, if the for the duration, right, during this daytime, it may so happen, for example, that in order to avoid shutting down these base load plants, right, a system operator may, or the plant operators may continue to operate their plant, but then the prices of the electricity may really go down, right? And these baseload plant may end up producing and selling power at a lower forced to sell power at a lower price than what it would take to produce that power, right? So they might incur some amount of losses during that period, just to ensure that the plant continues to operate, right? So that in the evening, when again demand becomes more, prices become more, they can probably make or compensate for that period. So such kind of challenges are there because solar is a non-dispatchable source. It cannot be, it cannot be controlled as easily as conventional generating plants, right? Yes, now people are discussing about adding storage, right, to make them make the solar plus storage, a combination of these two, as a dispatchable source. But there are quite a few challenges and so on which exist in those systems also. But yes, those are some of the solutions people are exploring. So this is if I say at grid level, this is one of the challenge, which is the low power demand during day and high during evening, right? So what is happening is essentially the peak demand still remains the same. Peak demand still remains the same, so you may still need to have a lot of conventional generations still physically existing, although they may not necessarily be asked to operate during the day. So it kind of, if they exist, at least let them produce power so that the overall thing become economical. But because the base load, because the afternoon requirements are low, they may not be operating also. So this is kind of one challenge. The other challenge which exists in the system is the reduction in the overall inertia. Now conventional generators, right, they are all mostly based on synchronous generators, and their rotors do have significant amount of inertia. And that is one of the reason that when a system transient comes in, right, kicks in, then the frequencies may not vary very suddenly. They would still vary, but then frequencies do not change very suddenly because of the inertia of these conventional generators. But the inverters, right, the power electronic converters, do not have any inertia as such, right? In fact, they operate with a completely different principle, and there is no concept of rotating machine which exists in inverters, right? Inverters are supposed to be acting fast, right? They do act much faster than the conventional generators, and therefore if there's a load change which happens, the frequency change might also happen very suddenly in these inverters if they are incorporated with loop controllers and so on. And if that happens, right, you see what kind of challenges can come. For example, if you imagine the scenario where there is large PV penetration, right, and this is the frequency plot. Let's say frequency was at 50 Hertz, and there was a transient which, in normal circumstances, when there was PV was low, there was more of conventional generators, the transient would have taken up and would have probably, let's say, settled, right? It would have probably touched, let's say, 50.1 Hertz. But now, because the system has lesser inertia, the same transient or some other transient, there's a possibility that the frequency during transient might go even higher, let's say 50.4 Hertz. So therefore, during transient, right, now this transient, for example, could be, let's say, some failure of a certain interconnecting lines, and then sudden separation of two systems or two subsystems of the grid. So such kind of transients can cause significant variation in frequency. Earlier it was limited quite a few due to the large inertia, right, or the capability of these conventional generators to provide much more power even during transient. But now if it is more of solar, that may not happen, and then the frequency might deviate more than what it would before. And now if you see the previous discussion, our earlier inverters, we have asked them to get disconnected as soon as the frequency goes above, let's say 50.2 or 50.3 hertz, right, over frequency. So what will happen now if this two systems get separated? There are frequency goes up. If you see, this is the point where inverter gets disconnected. Right, if inverters get disconnected, and if the inverters are the main power producing component in that subsystem, that particular region, then this would lead to further mismatch between the load and demand, right? And again, if the frequency tries to come back, inverters may not connect back, and this could, you know, all of this could lead to a catastrophic failure of the system. So this, you know, again is the second problem, which is kind of mix of, I would say, low system inertia and plus the over frequency disconnect, right? Over frequency OF disconnect. So this is again, you know, shows one of the challenges which might come because of larger solar PV penetration in the system. Okay, so yeah, what I've tried to show in this video are few of the challenges, right? If you go and see, there could be lot of other challenges which could arise in, you know, very specific systems, in specific scenarios, specific case studies, and so on. But this sort of sums up and gives us a basic idea about some of the challenges that exist when integration of solar into the system.